Hello everyone. The topic that I would like to teach today is in the course Discrete Mathematical Structures. Subject code is 18CS36 under Module 4 Principles of Counting. The topic name is Recurrence Relations. Myself, Dr. Madhura K, working as an assistant professor in the Department of Mathematics, Sai Vidya Institute of Technology, Bengaluru. Come, let us first learn the definition for recurrence relations. And in particular, under recurrence relation, we have two topics. One is the first order recurrence relation, and secondly, second order recurrence relation. First order recurrence relation we'll be learning in this class. A first order recurrence relation with constant coefficients is of the form an is equal to c into an minus 1 plus f of n for all n greater than or equal to 1, where c is a known constant and f of n is a known function. Suppose f of n is equal to 0, the function that you can see in equation 1. If f of n is 0, whatever the expression we have is an is equal to c an minus 1 gives us the homogeneous recurrence relation. Otherwise, it is called as the non-homogeneous recurrence relation. Let us note some of the points. The general solution of a homogeneous recurrence relation is given by an is equal to c power n into a naught for n greater than or equal to 1. So this is the general solution of the homogeneous recurrence relation. When do we obtain homogeneous recurrence relation? Is when f of n is 0 from equation 1. Similarly, for a non-homogeneous recurrence relation, the general solution is given by an is equal to c power n into a naught plus summation k equal to 1 to n c power n minus k into f of k. Again, it is valid for all n greater than or equal to 1. So these are the required formulas that we'll be applying when we do problems on first order recurrence relation. So let us see some problems. Solve the recurrence relation 6 into an minus 7 into an minus 1 equal to 0, where n is greater than or equal to 1. And there's a condition given a3 equal to 343. Let us do the problem. Firstly, analyzing the given expression, that is 6an minus 7an minus 1 equal to 0. We'll be able to write it down as 6 into an equal to 7 into an minus 1. We wrote it in this form so that we can write down what is the expression for an by dividing throughout by 6. We get 7 by 6 into an minus 1, which is a homogeneous first order recurrence relation, which is of the form an equal to c into an minus 1. So the expression f of n term is 0 here. So we have an equal to c into an minus 1. On comparison, we'll be able to write down the value of c as 7 by 6. Now, let us write down the general solution of this homogeneous recurrence relation, which is given by an equal to c power n into a naught. And this is the expression or the general solution for all n greater than or equal to 1. We substitute the value of C here and we get an equal to 7 by 6 whole power n into a naught. Still the work is not over. One of the initial value is given for us, that is a3 equal to 343. So we use this initial condition in equation 1, which will help us to find the value of a naught. So for n equal to 3, equation 1 becomes a3 equal to 7 by 6 whole cube into a naught. And simplifying by substituting a3 value as 343 from the given data, we get 7 by 6 whole cube into a naught equal to 343. Cross multiplying and simplifying will get the constant for a naught as 216. We substitute this initial value a naught in equation 1, which gives us the complete solution. That is an equal to 7 by 6 whole power n into 216. So not only obtaining the general solution, it is actually in particular, we are finding out the particular solution by substituting the initial value a naught. So this is one such example which I took up in the first order recurrence relation. Moving on to another problem. Solve the recurrence relation an equal to, an minus 3 an minus 1 equal to 5 into 3 power n. For all n greater than or equal to 1, given that a naught value is equal to 2. In this problem, the initial value a naught is directly given for us. Let's see how to solve the problem. Given whatever the given expression was there, we are just rewriting it by transferring minus 3 into an minus 1 to the right hand side. So we obtain an is equal to 3 into an minus 1 plus 5 into 3 power n. We observe this is a non-homogeneous expression, non-homogeneous first order recurrence relation, which is of the form an is equal to c into an minus 1 plus f of n. So we are able to compare it to the standard form of the first order non-homogeneous recurrence relation and obtain the value of c as well as the value of f of n. So on comparison, c value is 3 and f of n value is 5 into 3 power n. So that we'll be able to write down the general solution now, which is given by, this is the general formula, general solution expression. an equal to c power n into a naught plus summation k equal to 1 to n c power n minus k into f of k for n greater than or equal to 1. Now we will substitute the value of c and we can also substitute the value of f of k. F of n is known to us, so in the same manner we will be able to substitute for f of k. So c value is 3 power n, a naught as it is, I have retained. Later we will substitute the value for a naught as 2, 3 power n minus k into f of k. Now expanding the summation, where k takes the value from 1 to n, we get 3 power n minus 1 into f of 1 plus 3 power n minus 2 into f of 2, etc. up to when k equal to n, the upper bound, we get 3 power 0 into f of n. So that in the next step, we will substitute the value of f of 1, f of 2, f of 3, etc. from the known function f of n, which is 5 into 3 power n. So f of 1 will be 5 into 3 power 1, f of 2 will be 5 into 3 power 2, etc. F of n is written as it is 5 into 3 power n. We observe 5 into. 5 is a common expression in each of these terms. So I take 5 common. And we simplify these powers of 3 using a basic property. When the base are same in a product, the powers are added. So I have 3 power n minus 1 into 3 power 1. So since the base is common, in this product powers can be added. So minus 1 plus 1 cancels, I remain with 3 power n. Similarly, when I look into second term, 5 is already taken common outside. 3 power n minus 2 into 3 power 2. Base is same again in this product, so powers are added. Minus 2 plus 2 cancels, so we remain 3 power n again. So similarly, it happens for all the remaining terms. We observe the last term, 5 being taken common. 3 power 0 is 1 into 3 power n. So it's 3 power n. And we are adding this sum n times, so that we can write it down as 5 into n into 3 power n. Because 3 power n is added n times, we get n into 3 power n. Now simplifying this by taking 3 power n common, we obtain the general solution of the given expression. That is nothing but an is equal to 3 power n into 2 plus 5 into n. So did you observe that a naught value was substituted in the third step? So a naught is nothing but 2, which is the given data. From the given data, we have been substituted a naught value, which is 2. So this gives us the general solution of the given non-homogeneous first order recurrence relation. Now next problem, we'll consider a different one. A sequence is being given for us. We need to find out the recurrence relation and hence the general term of the sequence. So let's see how to do this. I'll read out the question. Find the recurrence relation and the initial condition for the sequence 2, 10, 50, 250, etc. Hence find the general term of the sequence. So very firstly, from the given sequence, we need to find out the recurrence relation and the initial condition associated with it. Then we'll be trying to solve that recurrence relation. So let's see how to do the problem. From the given data, that is given sequence, I can denote this in the form of notations, that is A0 is 2, A1 is 10, A2 is 50, A3 is 250, etc. Now we consider the differences between two consecutive values. So latter value minus the previous I consider. So I have A1 minus A0. When I perform A1 minus A0, we are getting 8. 10 minus 2, which is 8. Similarly, let us take A2 minus A1. That is 50 minus 10, which is nothing but 40. I can take one more difference, A3 minus A2. A3 minus A2 gives us 250 minus 50, which is nothing but 200. Now looking into these differences, we should be able to generalize and write down an expression in terms of an and an minus 1. So in order to write that down, I can represent these numbers 8, 40 and 200 on just a simple analyzation in these form. I mean to say that 8 can be written as 8 into 5 power 0 And 40 can be written as 8 into 5 power 1. The number 200 can be written as 8 into 5 power 2. So it was just a keen observation that each of these numbers were divisible by 8, and hence I took up in the form of 8 into 5 power 0, 5 power 1 and 5 power 2. So these expressions are now helping me to write down and generalize the expression. So we generalize it in the pattern as an minus an minus 1 equal to 8 into 5 power n minus 1. So how will we observe it as n minus 1 in the power is, I took up the difference in the form an minus 1. So each of these has a higher value first and then the smaller value. And observe that this smaller value is in the power here. So this is going to help us to understand that the difference is giving me 8 into 5 power n minus 1. So this is the recurrence relation with the initial condition a naught equal to 2. From the given sequence, we had already written what is the a naught value, no? So that same a naught value has been rewritten here. This was our first part of the problem, that we need to find out the recurrence relation along with its initial condition. Now let us proceed further to find out the general term of the sequence. Now adding all these above expressions, I had the differences, no? A1 minus A0, A2 minus A1, A3 minus A2, etc. up to AN minus 1. Let us add up all these expressions, which will give us an minus a0 in the left hand side, and the right hand side terms are added. 8 into 5 power 0 plus 8 into 5 power 1 plus 8 into 5 power 2 etc. up to 8 into 5 power n minus 1. So how did we obtain the difference in the left hand side as just simply a0 an minus a0 is because observe you have a1, and in the next term when you add it is minus plus of minus a1, which gets cancelled. Similarly, a2 gets cancelled along with the term minus a2 here. So the previous terms keeps getting cancelled. So you just remain here with an, and the very first term, that is a0, remains. So that is the reason we have left hand side as an minus a0. Now let us simplify the right hand side by taking common. We have 8 common in each of these expressions. So we take 8 common. We remain with 5 power 0, which is 1, plus 5 power 1 plus 5 power 2 etc. up to 5 power n minus 1. This expression is a geometric progression which is of the form 1 plus r square etc. up to finite term r power n minus 1, whose sum up to n term is given by r power n minus 1 divided by r minus 1, where r is greater than 1. So let us apply this geometric progression formula, that is r power n minus 1 divided by r minus 1, for the expression 1 plus 5 square etc. up to 5 power n minus 1. On comparison, r value is equal to 5. Substituting, we get an minus a0 is equal to 8 into 5 power n minus 1 divided by 5 minus 1. R value is 5. We just have substituted that R value as 5 here. A0 I will substitute at this stage. A0 value is 2, which is already obtained from the given sequence. 5 minus 1 is 4. 4 ones are and 4 twos are. So I remain with 2 into 5 power n minus 1. Taking this minus 2 to the right hand side becomes plus 2. And I have retained 2 into 5 power n minus 1 as it is. And I have on multiplication 2 into 5 power n plus 2 into minus 1 is minus 2. So the 2 gets cancelled. And the required solution or the general term of the given sequence is an equal to 2 into 5 power n. Hope you have followed this problem, which was different than the previous two. Now I'll take up a next problem, that's a fourth problem, which is a statement problem, which we will be able to represent in the form of a recurrence relation and solve it. First, let us read the question. The number of virus affected files in a system is 1000 to start with, and this increases 250% every 2 hours. So the virus affected files in the system is 1000 in the initial stage, and this is going to increase 250% every 2 hours. Use a recurrence relation to determine the number of virus affected files in the system after 1 day. So first we will write down the recurrence relation for this, and we solve that recurrence relation, which is later going to help us to obtain the number of virus affected files after a day. Let us see the solution for this. Given A0 value is 1000. So initially, to start with, there are 1000 affected viruses in the files. Let AN denote the number of virus affected files after 2n hours. We are generalizing, taking the AN term as a general expression to say it is the number of virus affected files after every 2n hours. We took it in the form of 2n hours because the given data is given based on 250% increment every 2 hours. So we are trying to multiply by n 2 into n hours. It is given that the number increases by 250% every 2 hours. So this can be represented symbolically as A1 equal to A0 plus 250% into A0. We have the expression, that is the next value. Initially it is 1000, no? So the next after 2 hours, this can become A1. So A1 will be given by initial value, that is 1000 plus 250% of the 1000. That is what it becomes. That is what the given data says, that is it is increasing every 2 hours. Keeping this in view, we can also write down for A2, which is A1 plus 250% of A1. Similarly for A3 is A2 plus 250% A2. And so on. So that these expressions can be generalized and written down as AN equal to AN minus 1 plus 250% of AN minus 1. Just a keen observation on these values. We will be able to generalize and write down the term for AN. Now this can be written as taking AN minus 1 common. It is 1 plus 250%. And 250% can be written as 250 divided by 100. So simplifying this expression, that is 1 plus 250 divided by 100 using a calculator, we'll be able to write it down as AN equal to AN minus 1 into 1 plus 2.5, which is 3.5. So this is how we obtain the recurrence relation, and we observe this is a homogeneous recurrence relation, which is of the form AN equal to C into AN minus 1. So AN equal to C into AN minus 1 is a homogeneous recurrence relation standard form, and on comparison C value is 3.5. So this gives us the homogeneous recurrence relation for the number of virus affected files. Thus, the general solution of the recurrence relation is given by, for a homogeneous recurrence relation, this is the standard form of the general solution, which is AN equal to C power n into A naught. Let us substitute the value of C as well as the value of A naught. C value is 3.5 power n, A naught is 1000. This gives the number of virus affected files after 2n hours. That is what we assume the expression for an in multiples of 2 we had to do, because for every 2 hours the increment, that is 250%, was mentioned in the question. So this is the general expression which is giving us the number of virus affected files after 2n hours. Now we are asked to find out after a day how many number of virus affected files exist. So number of virus affected files after a day, which is 24 hours, can be obtained by taking n equal to 12. We take n equal to 12 because when I take n equal to 12 in this expression 2 into n, I'll be getting 24. 2 into 12, which is 24 hours, which gives us 1 day. So since we had evaluated this expression an with respect to calculation is with respect to 2n hours, that's the reason we take n equal to 12 and obtain the answer. So A12 equal to 3.5 whole power 12 into 1000. Simplifying this using a calculator, we obtain 3.379 into 10 power 9 approximately. Hope you have followed these problems which I considered on first order recurrence relation. I've given some practice questions so that you can have more clarity on the first order recurrence relation. So these are your practice questions which will give you more idea. Thank you for watching.